All right, let's start. Is my screen visible to everyone?
Yes, sir, it is.
Yes, sir.
Okay, great. Hi, how is everyone?
Good.
Great.
Good, sir.
Great. All right, so I don't know why there's fewer participants today, but let's get started. We've waited 10 minutes, so let's just get started. Okay,
Sir.
sorry. I didn't catch that. Okay, let's get started today. I want to talk about a few things. Some of you might have already seen these ideas. That's okay. So the first thing that I want to talk about is we've been sort of, I sidestepped the conversation a couple of times, but let's do talk about this concept of, how big things are and the idea of infinity and what we really mean by this infinite idea. So let's start off from a simple question, which is if I give you a collection of objects, right? Let's say there's a few objects in there, perhaps a few shapes. And I ask you a question, which is how big is this set? How would you answer that question?
By counting the number of objects in the set.
Okay, so simply by counting the number of objects. So that seems a fairly simple idea, right? If you want to know how many objects there are, how big is the set, you just count the number of elements, and that seems to work perfectly fine. And this idea of counting, we're going to come back to is how exactly do we count? So this seems to work. And now if I give you a set, another set, and I put down another few objects, and perhaps I put in a couple of similar objects, and perhaps objects like this. Again, this is simple. You can just count. And then I move on from that idea and I ask you, how big is the set n, which is basically just a set of natural numbers, right? 1, 2, 3, 4, and so on. So we denote it by this 1, 2, 3, 4, and so on. This is one representation of the set of natural numbers. And assuming that we can construct such a set using some axiom, how would you tell me how big is this set?
Aleph null.
Aleph null. Okay, so something like this. So let's call it Aleph null. And before we get into that idea of Aleph null, could you just expound upon what you mean by Aleph null?
It's infinitely large.
Okay, so a simple answer is it's infinitely large.
Countably.
Okay, so let's add in another adjective here, which is infinitely countably infinitely large. Why did you feel the need to add in this countably infinitely large?
because we can kind of grasp how infinite it is. I'm explaining it rightly. We can count each one, but in another, we can make a representation with it and exhaust all the elements,
Mhm.
whereas in other things we can't.
Okay, so it seems that we might need a better notion of, we need to be a bit more precise about what we say, about what we mean when we say things are countable. And what we mean exactly is, what are we exactly doing when we're counting things? So at this point, it's useful to define this notion of, because, and this question you can extend to, when you ask how big is a set, how big is the set? And you can also ask the same question for how big is the set of integers? How big is the set of rational numbers, which is, so the integers included 0 and positive, negative natural numbers, and the rationals and the set of real numbers. All of them are sort of, we know that they're infinitely large, but it seems we seem to stop at this point that we just know that they're infinite, but are they the same kind of infinite is really the question that I want to approach today. And so it might be useful for us now at this point to define this idea of cardinality, which is, I'm going to start off by saying that it's a simple fact. I'm just going to state that for finite sets, their cardinality is simply the number of elements within the set. That's a very simple idea, and which we've been doing for the first two sets that I drew here, is when I drew them, you simply count them and you say, okay, this is 1, this is 2, this is 3, this is 4. So there's 4 elements in the set, and the cardinality is simply 4. And this one, again, you say 1, 2, 3, 4, 5, 6. And so now there's 6 elements, and the cardinality of this finite set is simply 6. So what I'm defining is a notion for the size of a set. And so for finite sets, this seems to be working perfectly until we go for infinitely large sets. And then counting doesn't seem to stop at some point, right? Because it seems that if I were to start counting the number of elements in the set of natural numbers, it's actually the same thing that I'm doing here, which is 1, 2, 3, 4, and so on, which is exactly the same as the set of natural numbers. So let's be a bit more precise about them. And now I'm going to redefine cardinality. Is in some way, I'm going to say that two sets have the same cardinality if there exists a one-to-one, so 2-1 correspondence between their elements. So what I mean by that is, I mean that suppose I were to make another set right here, which is a subset of the set of natural numbers. It contains simply 1, 2, 3, and 4. My original set on the left, and my new set on the right, which I'm going to use to count the elements on the left-hand side. So I say that there's a correspondence between this element and the number 1 here. And then I say that there's a correspondence between this triangle and this element and this square and this number 3 right here and this ellipse and the number 4 there. So there's a one-to-one correspondence between these two sets, and that's actually honestly all you're doing when you're counting. You're creating a one-to-one correspondence. And what I've just created, we call a mapping. And there's two properties of this mapping. This mapping is one-to-one, right? And you must have, I expect you have some idea of this correspondence, of this idea of a function being one-to-one or a mapping being one-to-one. And this idea of it being onto, which is these two in a different way, these are called the injective and surjective properties, right? And so by one-to-one, I simply mean that each object is mapped onto one object on the other hand side. There's no, so two objects. So if I create a mapping from, let's say, this triangle to this one, then this mapping is no longer a one-to-one mapping, okay? And suppose if I were to, so let me say where the mapping is going from. So the mapping is going from, let's call this set A to the set B. And let's say this is the direction of the mapping. And now if I make this mapping from the triangle to this one, this mapping is no longer one-to-one. This is another kind of mapping. I'd say this is 1, 1, 3, 4. That's not a one-to-one mapping, okay? A one-to-one mapping will always have unique elements from the left-hand side to the right-hand side. So let's say I draw it like this. And if I were to, stop here and create perhaps another element, let's say I add in a 5 here. Now, again, this is a mapping, which is a one-to-one mapping, sure, but it's not an onto mapping. And by onto, I mean all the elements on the right-hand side should be mapped onto by some other element from the left-hand side. But this number 5 clearly doesn't have a corresponding element on the left. And so now this mapping is no longer onto. So it's you can now get an intuitive sense that it's only one-to-one and onto if you always have the same number of elements. Otherwise, you don't have an one-to-one correspondence between the elements of the one set and the elements of the other set. Are these ideas clear to everyone?
Yeah.
Any questions on this, anyone? Feel free to ask now because I'll be building upon these ideas. Okay. Yeah. All right, so if I were now to create a set here of 1, 2, 3, 4, 5, 6, now you can, of course, create a one-to-one mapping between set A and set B. You just draw arrows, and it's the same mapping which I've actually, just by labeling these points, I've made this exact same mapping. And if you just draw the corresponding arrows, you've done essentially the same thing, okay? And so at this point, we find it useful to just define the cardinality of the set of natural numbers by the symbol that Ryan mentioned, which is the Aleph null symbol. We call it Aleph null. And this is the first kind of infinity that we encounter. And we call it the first kind of infinity because you can sort of, I say you can sort of count them, but counting is nothing but, corresponding with the set of natural numbers. So actually, we're starting off by counting. The mere definition of counting infinitely large set stems from the idea of the set of natural numbers. So that's my basis for the first level of infinity, the set itself, the set of natural numbers. And now, if I ask the very simple question of how big is the set of even numbers, how can we use this idea of cardinality to answer that question?
It has the same cardinality as the natural numbers.
All right, so let's call this the set of even numbers is E, and this set of natural numbers is 1, 2, 3, 4, 5, 6, and so on. From a simple perspective, if we were to use our intuition from the set of finite, the intuition that we have from the finite set, which is that if I were to remove, let's say, this object right here and this object right here, I subtracted two elements from the set, and what I get now is a smaller set. Right? That's what our intuition tells us, and it's actually quite obvious that if you were to take a finite set and you remove a few elements from it, you get a set that is a smaller set, right? So the cardinality is lower than the previous set that you had. But the same sort of idea doesn't seem to translate when you're thinking about infinitely large sets. Because notice that if I were to take the set of natural numbers, and if I were to systematically remove the set of odd numbers, from the point of view that we have for the finite set, you should kind of get a smaller set because you've sort of removed an infinitely large number of elements. But the number of elements that are remaining are also infinitely large, right? So there's 2, 4, 6, 8, 10, 12, it keeps on going.
Sir?
Yeah.
So isn't it possible that the set of even numbers is also countably infinite, but it's smaller than the set of natural numbers? Like an infinity smaller than the other infinity?
But then so you're saying they have the same cardinality, but you're also saying it's smaller. In what way is it smaller? Because my notion of size at this point for larger sets seems to be the only kind of definition that I can think of is, a correspondence in the cardinality of that set. So in what way are you saying that it's a smaller set?
So if I think about it, I have to make it a finite set then. I understand your point when you make that, but then if I say that the set of even numbers is smaller than the set of natural numbers, I have to think of them in terms of a finite set. And I don't think that logic transforms in the infinite realm.
So one way, yeah, it definitely doesn't, because now you can see the same notion of cardinality that we had, which was that you can create a bijection, right? That you can create a one-to-one correspondence, and it's actually quite obvious what that correspondence would be, that this element corresponds to this element corresponds to this element corresponds to this. And I can actually make this correspondence quite rigorous, which is that if I want to create this mapping from the set of natural numbers to the set of even numbers, it's actually quite obvious what it will be, is that I take the number n and I map it onto the number 2n. And I can prove that this mapping that I've just created is injective and surjective. That is, every element is accounted for and every element has a unique pre-image, right? So the pre-image of 2 is 1, the pre-image is 4 of 2, 6 is 3, 8 is 4, 10 is 5, 12 is 6. Okay, and we can actually go into this a little bit and actually systematically prove that these are exactly this mapping that I've created satisfies these two properties. But from an intuitive point of view, you can actually see it sort of, even though I've not drawn and not written down an infinite number of elements. And you could argue that at some point this mapping might break down because you haven't written down the infinite number of elements. But intuitively, I think all of you would agree that this sort of seems to be making sense, that any number over here that I have, any number n that I have will have 2n as its image, right? So one way in which you might want to say that E is smaller is maybe the notion of the E being the subset of the set of natural numbers. That is definitely one way in which you can claim that it is smaller, because every element of E is an element of the set of natural numbers, but every element of the set of natural numbers is not an element of E. So perhaps you can say that it's smaller in that sense, that it's a proper subset of the set of natural numbers. But as far as cardinality is concerned, the cardinality of this set is also this Aleph null cardinality. Okay. Actually, it's a sort of, I think it's drawn something like this. So let me draw it like, it's a very tricky symbol to print out. Okay, does that make sense? Does anyone have any questions here? No? And if I were to ask the same question for the set of odd numbers, what would be your response to that?
Fn is mapped into 2n minus 1.
Fn is mapped into 2n minus 1. Yeah. And so how about we go on and we prove actually that this map, so from the set of natural numbers to the set of even numbers, is injective. And before, of course, we do that, I need to define what injective and surjective mean. So for injective, I mean that so let's define a simple mapping. So consider an injective map. So a map F from a set A to B is injective if each element in B has a unique actually, I'm sorry, that's not how you define it. Is injective if, and let me state that if f of A equals f of B, then A equals B. And what I mean by this is actually, let me demonstrate this idea intuitively, that this is an element, this is a set A and this is a set B. And if I have a few elements A, B, C, now let's say A is mapped onto some element here, which is f of A, and B is mapped onto some element here, f of B. My claim is that it is injective if and only if their images are the same, the original elements must also be the same. In other words, if I were to claim that there is an entity here, let's call it F, or actually, let's not do that. Let's call it P1. Yeah. Let's call it P. So if A were mapped onto P, and B were to map onto P as well, then what I essentially have is f of A equals f of P, because they're both equals to P. However, if I check in my previous set, A is not equals to B. And therefore, this set is not injective, because P has two pre-images. One is A and one is B. So both A and B are mapped onto the same element. So if the images are the same, the element must also be the same. Does that make sense? This definition of injectiveness that I've written? Any questions about this? No? If it's not clear, please feel free to ask, because once we try to prove it, then it won't be clear to you how we're proving it. So can someone, if there are no questions for it, can someone help me prove this idea that when I create this map from the set of natural numbers to the set of even numbers, this mapping that I'm creating, f of n equals 2n, can you help me prove the claim that the map is injective?
If f of A equals f of B,
Mm-hmm.
then 2A equals 2B, which
Mm-hmm.
means A equals B.
That immediately means, because we can cancel out the 2's, we can divide the whole thing by 2. Immediately you see it's such a simple proof. It's 2 lines actually, that suppose if A, so all we're saying that suppose if there were 2 elements that had the same image, you know, let's call this P, right? They have the same image. Then if they have the same image, what are their images? Well, the image of A, according to this map that we've generated, is just 2A. And according to this map, f of B is just 2B. Then I can use simple division and say A equals B. Can we do it for this mapping that we had for set of natural numbers to the set of odd numbers? The mapping that we had was f of n equals to 2n minus 1. Can we do a same kind of proof for that?
Say f of A equals f of B, which is the same thing as saying 2A minus 1 equals 2B minus 1. You add 1 to both sides and then divide by 2.
Yeah. So again, it's very easy to see that this is an injective map, right? That if there were 2 images if 2 elements had the same image, they were actually not different elements. This last line is actually telling you that they were not, they can't be different elements. They're actually the same element. So this actually proving to you that this AB, if you were to make the claim that they're being mapped onto, if you were to suppose, for the sake of argument, that these 2 objects have the same image, then you would be forced to conclude that this is actually the one and the same element. It's not 2 different elements. Okay. So let's, is that clear to everyone?
Yeah.
Okay. And so let me just put down the definition of surjectivity. And then you can try to prove that definition on your own, perhaps. I'll leave it as an exercise to prove that the set of natural numbers, the mapping that you have from the set of natural numbers to the even numbers is a surjective. So suppose given a map, given f from A to B, how do you think we can define this notion of surjectivity, that every element has a pre-image? So in simple words, it's every element in B has a pre-image in A, which is to say that there must be some element in A. When you apply the function on it, it gives you the corresponding element in B. So how can I mathematically define it, given, this is the way I chose to define injectivity?
For all b little b in the set B,
Mm-hmm.
there exists a little a in set A
Mm-hmm.
such that f of a equals b.
Such that f of a equals b. So how can we prove such a statement for, let's say, the same mapping, which was n to e, f of n equals to n?
If I have an element of b, then the corresponding element a is b over 2.
And how? So okay. So if there exists b in B, right? So actually, let me say, given B in B, the corresponding element in A is simply B over 2. But now I have a question, which is that you're taking an element and dividing it by 2. How do you know that this element must be in the set of natural numbers? Because B over 2 could be, I don't know, 3 over 2. That's not in the set of natural numbers.
E is defined as the set of all x. If x is in the natural numbers, then 2x is in E. So that directly means that the division is also in the natural numbers. Division by 2 of a member.
Right. The only issue with that argument is that you're sort of saying that if there's an x in n, then the corresponding element is 2x in E, which is fine, but you're sort of saying that for every element in n, there is an element in E. The argument that we have to make is that every element in E has a corresponding element in n, which is actually, and you're sort of onto it, which is that it's actually, the idea is actually hidden in the way you define the set of even numbers. The way we define the set of even numbers is actually, it's actually the set of x such that x equals to 2n, where n is in the set of natural numbers. So given that if B is in B, by the definition, by the mere definition of E, it can actually be written as some element times 2. It's divisible by 2. Otherwise, it can't be any. And once you have that, you already know that it's divisible by 2, because now if I say A equals to B over 2, then it is simply 2 times n over 2. And so n, because n is a natural number, note that n is a natural number, so then we can conclude that A is that exact same natural number. So it's a very simple sort of a proof which you sort of have in your mind, but if you want to define it mathematically, if you want to make that argument, you have to be a bit careful about what you're stating. Okay, so you have to identify exactly where the truth that you're looking for, exactly where is it. And for us in this search activity, it was hidden in the definition of E. Okay.
Yeah.
All right, so these are very simple ideas, a set of even numbers, natural numbers. Let's level up a bit and let's now talk about the set of integers. What about the cardinality of the set of integers? I have 0, 1, 2 going in this direction, and then -1, -2 going in this direction. So the question simply is at this point, is the cardinality of Z the same as the cardinality of N, or have we actually found a bigger set now, at least in terms of the cardinality? Because it's clear that the set of natural numbers is actually a subset of Z, but we notice that that isn't enough for the cardinality to be bigger, because we found that the set E has the same property, but it doesn't have a smaller cardinality than the set of natural numbers.
The union of countably infinite sets is also countably infinite.
Okay, so the union of countably,
I'm just guessing. That's true.
infinite sets is also countably infinite. Now that's a statement that you'll have to, if I am to use this statement, I'll have to prove it. So can you prove this statement?
I can't think of any bijection from the naturals to the integers. So that's why I'm resorting to this.
Okay, so perhaps we can come up with a bijection. So the idea of finding a bijection is basically finding a way to count them, right? A way to count them is basically just trying to figure out how we can label them 1, 2, 3, 4, 5, 6, such that every element is covered.
I can order it as 0, 1, -1, 2, 2. Yeah. And that then I can count each.
Okay, so when you write it like this, going in both directions, it seems difficult to count them, because if you start counting it like this, 1, 2, 3, then you keep going in one direction, but you sort of miss out all the numbers in this direction. So it seems the right way of counting them is to count them sort of alternatively, which is to say this is 1, 2, 3, 4, 5, 6, and so on. So if you start alternating between the positive and the negative and the same idea, you can actually count them all, and you sort of have everything within your graph. So let me first draw this mapping, and then perhaps we can come up with a mapping that actually corresponds to this mapping. So this is the correspondence: 1, 0, 2 to this, 3 to this. Okay, so can I now define some quantity here such that it gives me a mapping from N to Z, which is a bijection, which encapsulates this bijection?
I think it would have to be a piecewise function.
Okay.
So if n is odd, then f of n is 1 minus that divided by 2.
So if n is odd, so what are you saying?
N minus
N
1.
minus 1 divided by 2?
Yes. And if n is even, it's n over 2. Oh, it's minus that.
Which one? The first one?
Yes.
Okay, so this is negative n minus 1 over 2 and n over 2 if n is even. So let's check your function for a few elements and see if it works or not. So if n is, let's say, even, so let's talk about even numbers. So for 2, it should be 1. So 2 over 2 is 1. That seems to work out. 4 over 2 is 2. That seems to work out. 6 over 2 is 3. So it seems at least for the even numbers, your mapping works perfectly fine. And let's see if it works for the odd numbers. So for 1, you said 1 minus 1 over 2, which is simply 0. So this checks out. 3 minus 1 would be 2 over 2 is 1. And then you added this negative sign. Great. So 5 minus 1 is 4 over 2. So that seems to work. It's just a division by 2. But for the odd numbers, you have to do two things, which is you give them an offset for 1. And then you plug in a negative sign to account that you're counting the negative numbers. And so again, this the same questions are still open, which is this mapping that you have just derived. Can you prove that they are injective and surjective? So you have to prove that F, show that, leave this as an exercise, show that F is a bijection. Right? Okay, great. So it seems like subset-wise, we do have a, even still countably infinite. You can find a way of counting it, and you still don't get a bigger set as far as cardinality is concerned. So far, nothing new. Let's try to go to an even bigger set, bigger by way of subset notation, the set of rational numbers. So what is the cardinality of Q? Is it now a bigger set because now you have all the rationals in it? So P over Q is now every element such that P is an integer. P and Q both are integers, but Q is non-zero, is now part of it. So not only do you have the integers, you have 1 over 3, and you have 5 over 7, and you have 9 over 11, and so on, right?
If there's a bijection between Z and Q, then it also has to be Aleph null.
Right. And why is that?
Because it
Right.
in
So you just,
turn
it okay.
has a bijection from N.
Right. So we've already shown a bijection between Z and N and E. The question is there a bijection here? Can we count Q in the same way that we counted Z? Can we do that bijection procedure or not? So I'm just checking the chat. I'm leaving early too. Okay. Please. Yes. So even the definition, yes. Again, if you're sending me a message, just feel free to unmute yourself and say it out loud. Okay.
The definition of Q already contains a function. It's multivariable. It depends both on P and Q.
Okay.
I know a way you can arrange them so it looks countably infinite.
Okay.
You start with 1 over 1,
Mhm.
then 1
Okay,
over
then
2,
arrange.
and
Okay, so you
and
start
then
off 1 over 1, 1 over 2.
and then below 1 over 1, there's 2 over 1,
Mhm.
and then 2 over 2 on that.
Okay.
And it continues on the bottom as well. So there's 3 over 1, 4 over 1.
Okay, so we sort of have this table now, this two-dimensional table where this side is talking about P and this side is talking about Q. So 1, 2, 3, and so on, and 1, 2, 3, 4, and so on. So we have this two-dimensional table, and we've sort of arranged them such that it seems like it should contain all the rational numbers, right?
Yeah.
Is it possible that we're missing any rational numbers?
The negatives.
Well, the negative numbers. So how do we deal with those?
You extend the table upwards and leftwards.
Okay, so let's grab this whole table and let's put it here. So what do you mean when you say you want to extend it upwards and leftwards?
Negative numbers go over the top.
Okay,
Above P and Q, over Q.
all right. So
Just
should
right.
I get rid of these? So let's say I was making a checker box, something like this. Okay. So where would you put negative numbers? So what would you, let's say I make a box here and a box here.
Yeah.
So what would you put here and here?
Above 1 over 1, I
Mhm.
would put negative 1 over 1.
Okay.
And next to that, negative 1 over 2. And
Mhm.
to the left of negative 1 over 1, I would put a negative 1 over negative 1.
Okay, so a negative 1 over a negative 1. And what would you put here then?
Negative 1 over negative 1.
A 1 over negative 1. So in the rightwards direction, what you're doing is you're sort of, this was 1, 2, 3.
I forgot the row for 0.
Yeah. So what will we do for 0? Where should I put the zeros?
Above 1 over 1, you get 0 over 1 and 0 over 2.
Okay.
To the here you would have 0 over 0, but that's undefined. So this whole column is
Okay.
empty.
This one?
Yeah.
Okay.
And then next to the empty column is the negative.
Mhm.
0 over negative 1, 1 over negative 1.
Okay. All right. So what's happening if people are confused as to what we're doing here is basically when we're going rightwards, we are increasing the denominator. When we're going leftwards, we are decreasing the denominator and the numerator remains the same. So for every row, the numerator remains the same. So the numerators are in the rows, so 0, 1, 2, 3. You can see that for every row, we have fixed the numerators. And the denominators are increasing and decreasing as you go left to right. Okay. And in every column, what we're doing is the opposite, which is we're fixing the denominator, which is 1. And we're sort of, when we go downwards, we increase the numerator and we decrease the numerator when we go above. So what should be this entry is I should fix the denominator, which is 1, and I should decrease the numerator, which is -1. So 0, -1, and then -2/1, and so on. And we sort of blocked out this column, and you can sort of think of it as hiding it, because what happens here is that you have to decrease the numerator, but if you decrease it from 1, you get 0. So anything over 0 is undefined. So we sort of marked this off as undefined territory, and that's not part of the rational numbers anyway, so we don't care. And actually, we don't even need to make this column because it's not part of the so why don't we just get rid of it and actually remove? So just to get rid of the useless column, I'm actually going to shift all of these entries here, because I know that this is not possible. And so now I have these entries which are 0 over -2, 1 over -2, 2 over -2, and so on. And so now it seems that if I were to fill out this infinite table in all 4 directions, like go in this direction, go upwards, go downwards, and go leftwards, and I fill out all of these infinite entries, I sort of have a checkerboard, and I have all of these entries, which I now, again, the question is, can we count it? Can we count all these numbers? And so even from a geometric point of view, it should strike you as something, an extension of dimension that has just happened, which was when you had the set of natural numbers, you were only going in one direction, and it was only the rightward direction that you had to count. So 1, 2, 3, 4, 5, and you keep going in the rightward direction. When we jumped to the set of integers, you sort of had 2 directions now, which was left and right. So you went alternatively between 1, 2, 3, 4, 5, 6, and you got all the numbers. And now a further extension has happened, which is now you have all 4 possible directions to move in. So right, left, up, down. And so sort of you have to find a way to alternate between these 4 directions if you're going to count them. Does that make sense? Okay, so the -1 over 0. Okay. So there's a lot of silence in the participants. So either that could mean 2 things in my experience. One, that you're understanding everything very easily, or that I have lost most of you. If it's the latter, please speak up and let me know where I lost you. And I have no issues going back to previous ideas. Can I get a vocal response from people? Is everyone on board? Hello.
Yeah, so for me, it's the former, not the latter. So
It's the former, so you're on board with everything.
yes.
Okay, great. Anyone else? Somebody writing in the chat then. Okay, so Saad Ahmed is on board. You're on board. Okay. Just going to start naming a couple of people if that's okay. Ayan, Fatma, Isha, are you all on board? Have I lost some of you somewhere?
No, you're here. I can hear you.
Okay, great. All right, so now the question is, how do we count these? And it's sort of, as far as alternating is concerned, the way that I can think of is to go out in a spiral sort of. If I start counting like this, I say I start off from this 1, 2, 3, I only go in one direction, and then I have missed out on the other direction. If I do what I did in the set of integers, which was 1, 2, 3, 4, 5, 6, and so on, I cover 2 directions, but then I miss out on the other 2 possible directions, which is a lot, right? And so now I have to find sort of a way to count all of them in a sort of spiraling out sort of a way with something like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, 17, 18, and so on. So you see, what I'm trying to do here is actually I'm trying to cover all of these numbers, and it's sort of drawing a spiral, something like this, that I go to adjacent numbers and I move out in this spiraling sort of a direction. And it is now intuitively perhaps clear that this spiral direction covers out all the numbers, but writing down a mathematical function for this is a bit more not as easy, at least as far as the natural numbers and the integers were considered. So for the natural numbers and even numbers, we came up with that simple mapping x equals to n. For the integers, Rhyme helped us make this piecewise sort of a mapping. And now it seems, again, it might be some sort of a piecewise mapping or some sort of, we'll have to find a way to make that mapping work. But intuitively, as far as the argument is concerned, it's sort of the same sort of mapping. So as far as you can put it into an infinite list, you can cover out all the numbers. And actually, what I think is a simpler way to do this is actually just to deal with the table that did contain the natural numbers. So here's my argument. If I just deal with this and I say this is countable, then I can actually extend the result to this infinitely large table. Can you see why? That if I were to prove that this arrangement, this set of positive integers, positive rationals, if these were countable, if Q, let's say, I'll put a positive sign above it to indicate that it just contains a positive number, is countably infinite, then so is Q negative. Can you see why? Can anyone help me make that argument?
We can see that Q plus is positive because you go to 1 over 1 to 1 over 2 to 2 over 1 to 2 over 1 over 3, then 2, something like that. Yeah.
Yeah.
And we could see if Q negative would be the same by putting negative signs in front of all these.
But how do I then extend and say that if both of, so it's very easy to see I put a negative sign for them, so is Q negative. But what about the set of rational numbers which includes Q positive, union Q negative, as well as union the 0?
Well, I could start off with 0, then pick something from Q positive, then Q negative, then Q positive, Q negative, just like with the integers.
Exactly. So if you can find a way to count even one of them, you found a way to count their union as well. Because let's say you found a way to count them, and I draw an exact replica of this exactly same table and just put it right here, a smaller version, which, where'd it go? All right, my window crashed for some reason. Give me just a minute. All right, we are back. So I was saying that if you have this corresponding entity Q negative, that this green lines that I've done are actually a way to count them. So if I were to count them, that's 1, 2, so if I were to count them as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on, I could actually make, and if I could do the same for this one, which is put a negative sign here, and negative, 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 all of these are. All right, seems like there was an internet connectivity problem. Are we back? Am I audible to everyone?
Yeah.
Great. Okay. And what was the point where the internet disconnected, so I can continue there?
You were talking about putting negatives in front of the table.
Okay. So these are all the negative rationals and these are all the positive rationals. And so I can count them like this, and I can count this one exactly the same way, which is start from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. If I wanted to do both of these tables together, the simple idea is I keep jumping back and forth between the two, just like I did in the set of integers, which is start from 1, then 2, then 3, then 4. So I'm following the same orange and green paths, except I'm doing them alternatively. The paths are already made for me. I just have to jump between these two paths. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and so on. And if I have, and this is just a geometric intuitive argument, we could make it rigorous, but it almost seems it's not necessary to make it as much rigorous than this, right? It sort of seems obvious, but you can of course do that. Is this clear to everyone? And of course, the small matter of counting 0 is just to do it at the start. Start off with 0, and then you do the jumping between the two sets. And so since you can count them, then the cardinality of Q, and let me make this a symbol, the cardinality of Q is also Aleph null. Everyone on board with that? So it seems like we have in some way bigger and bigger sets, but it also, another important way, they have the same cardinality. There's a bijection between these two, and there's a bijection between these two. So almost it seems like you lose or you gain nothing as far as extra elements are concerned when you just go from the set of even numbers all the way up until the set of rational numbers. And so the natural question to ask at this point is, does this pattern continue when we go to the set of real numbers, which is you add in the set of irrationals? Do you still get, so all of these sets were countably infinite? And does this story continue for one further set, which is the set of real numbers?
It doesn't.
It doesn't. So something happens, something dramatic happens when you go from the set of rationals to the reals, and suddenly you can't count the set of real numbers. So I'm going to state this as a fact at this point, that this set is actually uncountably infinite. This pattern, that nice little pattern that we had, that is the same kind of infinity, you can just count them, count all of them, suddenly fails once you go to the set of real numbers, because as soon as you, and the way it sort of appeals to me, sort of makes sense to me, is to say that if you start off from 0, what we were almost doing at this point was to ask, when you count, is you're actually asking yourself a very simple question, which is, what is the next number? That's essentially what you're doing when you're counting, right? So when you're counting the set of natural numbers or the even numbers, you're saying, what is the next number? The first number is 2, second number is 4, third number is 6, and so on. When you counted the integers, you said first number is 0, second is 1, third is -1, fourth is 2, and then -2, and so on. Again, for the rationals, same thing. First is 0, then 1 over 1, 1 over 2, 0 over 2, and so on. And that sort of simple question, which is what is the next number, becomes really difficult to answer when you talk about the real numbers. If I start off from 0 and I say, what is the next number? How can I answer that question? Is there a next number? Because there's so many things to consider. You could say the set of natural numbers, 1, 2, 3, and go on in that direction. Or you could cover the integers and -1, -2, and go in both directions. Or you could do what you were doing with rationals, except there is this new level of infinity of which zooming into that we talked about in the previous session, which was once you zoom into in just this, there's a whole different level of infinity right there. So do you say the next number after 0 is 0.1, or is it 0.001, or is it 0.000001? And just to look at that infinitely, smaller and smaller numbers, there's a whole level of infinity right there. So how do you even begin to count the set of real numbers? So that's one way, but perhaps it's still possible. Let's say you can sort of put them in a list. So let's say if you could count them, if I were to count down every real number, then I would sort of have a one-to-one correspondence between them, between the set of natural numbers and the set of real numbers. The first number, there must be some first number if they were countable. If they were countable, then there would be some first number, some second number, some third number, some fourth number, fifth, and so on. And well, this number, the first number could be 0.0000, and all zeros perhaps, and the second number could be 0.10000, and so on, or 1.20000, and so on. 2.13427, so on. And you have your pi in here as well, and you have your e in here as well, 2.17, 2.71, and so on. If it was possible to count them, then there must be some sort of this list that you could make, that these are all the real numbers, and these are exactly the same. Except we have a nice little diagonalization argument. We have a argument that says that you can't have, that this list is incomplete. This list is missing at least one real number. Is any of you familiar with that argument?
Cantor's diagonalization argument. So
Which is
if we look at the first digit of the first number, if it's zero, then I'll write 1.
okay.
If it's a non-zero digit, I'll write 0.
Okay.
So I look at the first digit of the first number, then the second of the second, third
Okay.
of the third, and I'm writing down my new real number, which is obtained by switching the numbers for 0 or 1.
Right.
And that
So
number can't be in the list because the first digit is different from the first number. The second is different from the second number. The third digit's different from the third number. So it can't be in that list already.
right. So what if I just add it to the top of the list?
Then I could repeat the argument.
Right. So the simple argument is you go down the diagonal of this list and you replace every digit. If it's a 0, you replace it by a 1. And if it's a non-zero, then you just write 0. So the new number that I've created is 0, 1. So I changed this to 0 to 1, and I changed the 1 in the next number. So I'm talking about now the second digit of the second number. And I change it because I notice that it's a non-zero. I write a 0 here. Then I go to the third digit of the third number. Notice that it's a 0, so I write a 1. Then I go to the next digit. Notice that it's a 4, so I write a 0. And I continue this process. And I come up with a new number that's 1.0100. And the argument is that this number was not part of the original list. And the reason it's not part of the original list is because we went down the infinite diagonal and we basically switched out all the numbers. So if this number was at the 1000th position, if that's your argument, I'm saying that this number is definitely different from the new number because at the 1000th place, whatever entry I had, I actually switched that to something else. So if it was a 0, I switched it to a 1. And if it was a non-zero, I switched it to a 0. That means at least one digit of this new number and the 1000th number has to be different, which means they're not the same number. So this number was not part of the original list. And so it's missing at least one real number. So we conclude that actually no such list can exist that can be counted in this way. And so for the first time, we encounter a set that's actually a different level of cardinality than the set of, there's no bijection here. So it's a bigger set, and now it's a bigger set not only in the sense of being a subset, but also in the sense of having the bigger cardinality, that you can't even count these numbers. So we've sort of gotten ourselves from two simple categories between a finite and the infinite. We now have a slightly more nuanced notion, which is even the infinite has at least two categories. One of them is countable, the other is uncountable. It's an infinity so big that you can't even begin to count it, right? Okay, so we've gone time now, and I think this is a good place to stop. I did want to talk about some other ideas last time. Okay, so any questions on this? We've talked mostly about cardinalities and infinities, and I would perhaps I can leave you to search for, but something that I wanted to talk about today, but I missed out on it, which is the idea that there's an infinite number of primes. You can check out the proof for that infinite number of primes. And perhaps you could try to prove that yourself. And I wanted to talk about paradoxes and primarily set theory a bit, and actually Russell's paradox. But clearly we've run out of time. So I'm just going to leave these as topics for you to explore on your own. And feel free to get back to me if you want to discuss anything that we discussed in today's class, or anything that you read up on over these topics and you want to discuss. Okay, that's it from my side. Any questions, comments? Let me just quickly check the chat here. Okay. Nothing else?
No, sir.
All right. Hope so that's the end of the week for as far as logic is concerned. Hopefully you have some idea now of making mathematical arguments, of seeing proofs, how they're done. We did a couple of proofs, and we looked at some of the foundational aspects of how you start building things from the basic ideas and getting more complicated systems and questions about the sizes of things and so on and so forth. All right, that's it. And next week, Dr. Danish will be continuing on the continuing this summer school, and he'll be talking about graph theory, I believe. And then I'll be taking over in the last week. All right, have a good day, everyone. Bye.